Chapter 6, Queuing Models, Part 2 of Section 1. So let's see how we identify and show a queuing model. So this is the format that we use here. This format includes 5 elements. Okay, the first one, A, is for interarrival time distribution. Okay, and the second one, B, is for service time distribution. And the third one is C, the number of servers, and then N as the system capacity, and at the end K as the size of calling population. Okay, so for the A and B, these are the common symbols. M is for exponential or Markov. So when we have exponential distribution for interval time and service time, we use M. M comes from Markov or exponential distribution. And if the interval time or service time is deterministic, is constant, you show this by D. Okay, and EK for Erlang with order K, PH phase type, and H hyper exponential, G arbitrary or general, and GI is general independent. Okay, so here are we have the well-known queuing models. MM1. MM1 means the first one, M, means that interarrival times is exponential. Then the second M means the service time is exponential. And then the third one, which here is 1, this means that we have just one server. So this means that we have a single server model in which that interval times and service times both are exponential. So we had this example before, right? In chapter 2 and chapter 3, you remember that. Or MMS, again, interval time is exponential, service time is exponential, and we have S servers. So it's multiple server model, the Abel Baker model, right? In chapter 2 and chapter 3, you remember that. So again, that's a queuing model in queuing theory, and we show that by MMS. Or MG infinity, this means interval time is exponential, service times is general, like a discrete empirical distribution, right? And we had it before again. And infinity means we have infinite number of servers. Or MG1, exponential for interval time, general distribution for service time, and we have just one server, single server model. Or GI-G1 as well. Okay, and these are the notations that we use in queuing theory. So the lambda here is the arrival rate, lambda E is the effective arrival rate, mu here is the service rate per server, and rho the system utilization rate. AN is the interval time between the nth and n minus 1th customer, and Sn the service time of the nth customer. Okay, and these are the system variables for a queuing model. LT, the number of customers in the system at time t, LQT, the number of customers in queue at time t, WN, total time spent in system by nth customer, and WQN, waiting time of the nth customer. Okay, and these are actually the typical performance measures in a queuing model. Pn is the steady state probability of having n customers in the system in long term. Okay, and Pnt, probability of n customers in system at time t. So the Pn is in long term, but Pnt is at time t. Okay, and L, here's a long run time average number of customers in the system. So long run time weighted average number of customers in the system, it's L. And LQ, you know this, right? You calculate this in your assignment 1, I guess. Yeah, assignment 1. So long run time average number of customers in Q. Okay, and W long run average time spent in the system per customer, and WQ long run average time spent in Q per customer. Okay. So now let's see how we can calculate the long run measures of performance of a queuing system. Okay. Average number of customers in system L. Let's see how we calculate this measure. Here we assume that we have a system and we have the LT, the number of customers in the system over time, and we have T as 20 minutes, let's say. Okay, so I see here, for example, here we have one customer for T1 for 2 minutes, for example. So T1 is the length of time that we have one customer. So here Ti is denoted by the length of time that we have I customers in the system. So for T1 we have 2 minutes here. We have another 2 minutes here for one customer. Again, we have 4 minutes here for again one customer, and another 4 minutes here again for one customer. So in total we have 2 plus 2 4 plus this 4 8 plus this 4 12. So in total we have 12 minutes that we have just one customer in the system, right? So now how we calculate the time weighted average number of customers in the system. So if we multiply I by Ti, I mean I customers in the system, then multiply the time that we have that I customers in the system. So, and then we take sum over I, all customers, and then divide this by T, the total length. So that will be an estimation for L. So L here is actually for a long term, but L hat can be an estimate for that long term measure. Okay, so here if let me show in this graph, if I multiply this one by T1, so that will be a rectangle here, right? It will be the area under this curve. So again, we have another rectangle here, including one customer here, another rectangle here, including again one customer, and another rectangle here, including one customer. Okay, and for two customers here, we have that show by a different color here. So here we have two customers, and again here we have two customers, right? And here we have just three customers in the system. Okay, so when we multiply the I by Ti, actually we are taking the area under LT, right? As you see here, right? So because of that, here we have L hat as 1 over T, an integral from 0 to T of LT dt. So this means that area under LT divided by T, that will be the L hat as well. Okay, so yeah, these two equations are equivalent. Okay, and when T goes to infinity, then L hat will approach to L as the measure for long term. And similarly for L, we can calculate the average number of customers waiting in queue by waiting in queue actually, okay, not in system. So LQ hat will be like this, exactly with the same one, but we have TIQ, the time that I customers waiting in line, instead of having I customers in the system. Okay, and again with the same manner for LQ hat and so on. Okay. So here, let's say we have a GG1NK system, okay, and we want to calculate the LQT by having the LT. So the LQT in general will be defined like this. I mean, if we subtract the LT by 1 in the single server model, then the resulting quantity will be LQT. Okay, so if we do this, I mean here we subtract the quantities by 1, then we will have this graph. So as you see here, this is for LQT. Okay, the first one is for LT, the second one is for LQT. So here, when we have one customer in the system, this means that this customer is in the server, right? So there is no one in queue. Here we have 0 customer in the system, so no one in queue as well. We have again one customer in the system, again no one in the queue. So this means that for the first 5 minutes there is no customer in line. But at time 5, we have 2 customers in the system. This means one customer is in the queue, right? And then from time 7 to 8, we have 3 customers in the system. This means that we have 2 customers in the line, and then after that it drops to 1 customer in the line, and then it drops to 0 up to the end. So this will be actually the graph for the number of customers in line, in waiting line. Okay. So as you see here, the TQ0, the total time that we have no customer in line in the queue is 5 plus 10 or 15 minutes, right? Yeah, 10 minutes here. Let me show with a different color here. Yeah, 10 minutes here and 5 minutes here. So that will be 15 minutes that we have no customer in queue. So TQ1, I mean the total time that we have one customer in the system. So let me show with another color here. Yeah, here we have 2 minutes that we have one customer in the line, and another 2 minutes again we have one customer, so it will be 4 minutes, right? And TQT, we have just this 1 minute as for 3 customers in the waiting line, right? So if we calculate the average, the time weighted average number of customers in queue, then we need to multiply the number of customers by the time, right? So 0 times 15, 1 times 4, 2 times 1, and then sum up, add up these numbers and then divide this by 20, right? It will be 0.3 customers. So this actually is this area, right? I mean the area under the LQ, right? LQT, okay? The average time spent in system per customer. So for W here, as you see here, W1 means customer number 1 spends W1 time in the system, which is 2 minutes, right? W2 is for customer 2. It spends 5 minutes, right? From 3 to 8. And W3 is for customer number 3. As you see here, customer number 3 arrives system at time 5 and then departs the system at time 10. So 5 minutes this customer is in the system. And customer number 4 arrives the system at time 7 and then still is in system up to time 14, right? And customer number 5 arrives the system at time 16 and departs at time 20. So here we have the time spent by each customer in the system. So if we add up all the time, all the spend time of customers and then divide it by n, the total number of customers, that will be W hat, an estimation for the W in long term, right? The average time spent in system per customer. And we can do the same for the average time, average waiting time. So here we have WQI for customer I. So we add up all those waiting time and then divide that sum over the total number of customers n. Okay, so and that's it. So this was part 2. In part 3 we'll see more details and concepts of queuing models. Okay, thank you.